we'll have examples. Okay, so on techniques of integration, the first lesson that we did was learn about the integral of a function that yields a natural logarithmic function. So the integral that we're talking about here is the u written in the denominator with its derivative on the numerator. That's the integral of the du over u. If everything is complete, the integral will result to a natural logarithmic function, which is the ln of u plus c. One very important thing that you need not to forget about here is that the derivative of the u that is written in the denominator should be complete in the numerator. So should there be a need for you to multiply by a constant, you need to do so. And correspondingly, whatever constant you have multiplied here, you need also that same constant to be divided or written as its reciprocal before the integral sign. That way, you have not altered the original integral. That is in the case of the first function that we discussed. So I will not anymore do that. Now, we also discussed the integral of the exponential function. This is the natural exponential function e. Now, the exponent of such an e is represented as u, and we can have its integral as the exact exponential expression given, provided that the derivative of the exponential u or the exponent u should be complete here as in terms of du. Again, if it's not complete, if you only need to multiply it with a constant, you need to complete it. That way, you will have the exponential function's integral as the exponential function itself. So all you have to do is copy it. And you were provided with an example for that as well. Next is the general exponential function. General in the sense that this time it's not an e expression, but rather an a raised to u expression. The a here, you have to understand, is a constant. And just like the natural exponential function, the derivative of the u, which is the exponent of your constant base a, should be complete. So it's au du, telling you that in here, you have the derivative of the u expression. The only difference of the integral of this general exponential function from the natural exponential function is the 1 over the ln of a, which is being multiplied to the au, the original given general exponential function. So in terms of treatment, we treat these two expressions, the natural exponential function and the general exponential function, in the same manner. The only thing is that we need to multiply by a constant 1 over ln of a for your general exponential function. Okay, so this is for the first set of slide that we had. Now, the second set of slide that we had is this, which I had recorded, and this one is very lengthy. I'm sure you had difficulty following through, just listening to it once. So, based on my recording, I recorded it for more than an hour. So you have to really read through, listen to it again, read through it again, and you have to practice solving on your own based on the topics that were written on this slide. Although I have labeled this slide as part 2 of the techniques of integration, specifically mentioning trigonometric functions, the last part of the slide talks about integration by parts. That is for those that have already listened to the entirety of the slide. So in here, when we speak of trigonometric transformation that needs to be done to a complex trigonometric expression, there's a need for you to review your trigonometric identities because they're very important in this case. Second, after reviewing your trigonometric identities, there's a need for you to know the cases or the different transformations that should occur first to your given complex trigonometric expression before you can even perform the integral process. Meaning, transform it first into a form wherein you are now ready to integrate the trigonometric expression based on the formulas that were provided to you on the first module. And that is the formula on integral of simple trigonometric functions. So you need to first have it transformed. And I think if my memory serves me right, there are around 7 types of transformation. So the first type that we discuss is the sine and cosine function, in which the exponent could be either odd and positive or even and positive. So in this particular type, it is important that you understand that the exponent is not negative. It should be positive for both. It could either be odd in the case of case 1, and it could be even in the case of case 2. So if it's odd, you need to split. You need to split. You set aside one trigonometric function, either cosine or sine. That way, the remaining trigonometric function can have its derivative in that form of that function you have set aside. I have discussed this as well. So you set aside one sine in this case, one cosine in this case. That way, when you distribute it already to the original expression, you have now the derivative of the sine and the cosine. In the case of the even exponent of the sine or cosine here, you have to use these identities. Okay? So they are similar in terms of form. They only differ in the sign that separates the 1 and the double angle cosine here. So in the case of sine squared, it's a minus. In the case of the cosine squared, it's a plus. Both are divided by 2. Now, in the case of sorry, I'm not projecting. So in the case of type 2, you don't have a single sine or a single cosine raised to an exponent, but rather, yeah, you have the product of the sine and the cosine. So case 1 is when m and n is odd. Of course, again, both should be positive. And in case 2, both are even. So case 1, either of the two is odd. And in case 2, both are even. So if both are even, you have to use the same identities that were presented to you in type 1. Type 1, wherein you're only provided with a sine or a cosine in your integral. In the case of case 1, you have to set aside one sine or cosine expression here, and the remaining sine or cosine, whichever applies, is shall I say, multiplied to that set aside cosine or sine. That way, your sine or your cosine expression will have a paired derivative to it. So, kumbaga sa ating lingwahe, nagkuha ka isa para mas stand na siya nga derivative sang nabili nimo. It's in the case of this one. And we have also examples of that given in this slide. Type 3 is when you are provided with a tangent or a cotangent. Again, the exponent should be positive. Okay? So you have to split your tangent into a tangent squared of x. The rest is standing alone. Like if you have a tangent to the fifth raised tangent of x raised to 5, you set aside the tangent squared, you keep the tangent cube. The purpose of setting aside the tangent squared is you will convert it to the second squared x minus 1, its equivalent identity. Question is, why will you convert the tangent squared which you have taken away from the tangent raised to m? It's because the second squared is a derivative of the tangent that remained, which you have split apart from the tangent squared. So you have again made sure that the derivative of the remaining tangent or cotangent, for example, has its derivative multiplied to it, either a second squared of x for the tangent and a negative cosecant squared of x in the case of the cotangent. So what is written here is just the identity equivalent for the tangent squared of x. You can also have a cotangent squared of x identity. Both are derived from the sine squared of x plus cosine squared of x being equal to 1. So you just either divide by sine squared or cosine squared depending on what particular identity you want it converted to. Okay? Now, that's in the case of type 3. Now, type 4 is now a combination of the tangent with a secant or a cotangent with a cosecant. So if you notice, the secant is actually the derivative of the tangent, and the cosecant is the derivative of the cotangent. So in here, it's a matter of setting aside the appropriate derivative for the remaining expression that you have in your integral. Meaning you have to set aside here a cosecant squared x. That way, this cotangent of x raised to m can be process using power rule because the derivative of that is negative cosecant squared x. The rest of the cosecant squared here, you need to convert to the cotangent. That way you have a cotangent paired with a cosecant derivative. The same principle you will apply for the tangent and the secant. So for case 1, if m is odd, then n is any real number. This n could be any real number, and this one is odd. So it could be that the tangent squared here will be set aside or split, or it could be that the secant squared here should be set aside and split into two and convert the remaining secant to an equivalent tangent. Um, I'm sure you have a hard time following what I'm saying here if you're not going to write down all of those in the form of practicing and solving exercises. But that's just how you do it with the case of this fourth type. Now, if it's even and positive, this one is odd. If this n is even and m is any real number, you have to split also your secant, the provided secant here, into secant squared x, which I already mentioned a while ago. You have to just remember, class, always that if you intend to use the power rule in your existing function, make sure that you have paired it with its derivative, and that's the secant squared. So, must split ikaw, just like what is dictated here. That's the same thing with the cotangent. You just make sure always that the function in which you're going to use power formula 2 should have its derivative together with it. It's multiplied to its derivative. That's in the case of case 4 and case 2, the product of sine cosine. Now, case 5 is when you have a standalone secant or cosecant. Now, if it's a secant or cosecant, the same rule applies if you have case 2 under type 4. So there's a need for you to split your secant x raised to n to secant squared x, and then the remaining should be interpreted or converted to tangent, whichever applies, as long as you have already the secant squared in here set aside. You have to understand that the identity that you can use here is this: the secant squared x being equal to 1 plus tangent squared of x. That is in the case of type 5. In terms of 6, so you have now a similarity with the product of the sine and the cosine in type 2, if you recall type 2 a while ago, but this time the arguments of the sine and the cosine are not the same. What do you mean, Miss, with the arguments? Ang theta ba lang nga gina-represent nga nakasulat sa sine kag cosine, that's the argument. If the constants being multiplied to the variables are not the same, then you cannot use the transformation procedure that is done in type 2, but rather you are to use this identity that whenever you have sine mx multiplied to cosine nx, where m and n are any real number, it's equivalent to this: 1/2 of the sine of the sum of m and n plus the sine of m minus n. Remember, class, this m and n are just constants. So if there's an x here and there's an x here, to integrate this, you just have to multiply your integral by that constant to complete the derivative of the theta. Divide also the integral by that same constant. So what you're doing here is converting a complex product of sine and cosine with different arguments to a very simple integration procedure, because in here, you have the constants here in the arguments of m and n, or sine and cosine, being added and subtracted here. So when you integrate this is very easy. Let's say, for example, if the sine of m plus n is the sine of 2x, may x na di class ha, may x, then that's just the cosine of 2x. That's just the cosine or the negative cosine of 2x, provided that you complete the derivative. So you need to assign 2 to the derivative and place another 1/2 before the integral, which we also discussed during integrals of trigonometric functions. Okay? Now, we have discussed here examples on the type, but after here, we have ended these complex trigonometric expressions with inverse trigonometric functions, integrals yielding inverse trigonometric functions. Okay? In the case of arcsine, arctangent, and arcsecond, and we have this whenever the constant here is not 1. You have to understand, because this particular integral is very limiting because the constant here is always 1. What about if this constant is 2 or 3? If it's 2 or 3, like this is 3, this is 2, this is 5, example, this is the formula that you will use. Okay? You just have to simply represent the constant here by its square root. So if a is 3, then this one is 1 over square root of 3, because it's a here and this is a squared. Okay? I think this one is more, if you're going to memorize, is more practical than memorizing this, because this one only works if it's a 1. If it's not a 1, then you will have this. If it's a 1, then you just change all of this to 1. You only need to memorize one set of formula that will be applicable for these two cases. This one will only have a 1 and 1 being added to or subtracted from the u squared, whereas this one could be any number for that matter. Doesn't have to be a perfect square, if I may say. It could be any real number. As long as, by the way, it could be any real positive number. Hindi pwede negative, kaya kita square root sang negative. Now, and then after here, we have discussed the by parts. Now, if you're going to ask me for the CHE specifically in here, and even if you're an ECE or if you're in other course, this one is very, very important in differential equations, because you do integration by parts in differential equations. And some of the problems, the worded problems, require that you know how to apply integration by parts. Now, question: when, Miss, do we use integration by parts? If you have a product of different functions like exponential trigonometric, algebraic exponential like x e raised to x, algebraic logarithmic like x ln of x, as if you have a product of two different expressions, two different functions, we always suggest you use integration by parts. That way, you can choose a u, get its derivative, that would be your du, and you can use, and you can, the other part would be the dv, the remaining expression, and you integrate it. Once you have these four, actually what you only choose is the u and the dv. These two will just follow if you have already chosen the u and the dv. If you have chosen the u, get the derivative. If you have chosen the dv, get the integral. And you follow the formula that is provided here. That's uv minus the integral of v du. And I have examples here. So you are differentiating here, you have integrating, you are integrating there, and this is the sample. And the rest are all using integration by parts. So algebraic trigonometric. The other one, the example 2 is algebraic logarithmic. The example 1 is algebraic trigonometric. So a product of two different functions. So it's advised that you use integration by parts. So our goal this afternoon is we can have more examples on this. That way it would be easier for you to recall what you need to apply. Because you only get to, if I may say class, you only get to master something if you repeatedly do it. And the process of repeatedly doing it, you'll be realizing that it's better if I do it this way, or this one is longer while this one is shorter. So you know which particular method applies for you. It's like you become a master on something that you practice doing continuously. Okay, so I will now go to the whiteboard. That way we can have sample problems that we can process using those that I have reviewed. So we reviewed for 30 minutes. Let me share something here. Integration, no, that's not hyperbolic. I will have geometric. Okay. This is a summary of the things that you need to, if I say memorize and understand, identities, all of these are identities that they will help you integrate. But in the last part here, you will have problems to process. So let's say we'll have, can you see what I have here? Do you see what I have there, class?
Yes, miss.
Okay, so I'll go to the board and we can try solving this. Or we can try here. If the space is enough, we can have it here. Okay, I will just annotate. Okay, so this is sine of 3x. If you're processing this, this will require that the argument of the sine should have its derivative here. So the derivative is 3 dx. Since you have already introduced 3 here, there's a need for you to place 1/3 here. Or it's equivalent to multiplying your original integral by 3 over 3. So it did not alter the integral at all. So in this case, you will have now, so your answer is the negative cosine of 3x. So this one is just using simple trigonometric formula in integrating. So we start off with that. Now we go to this one, the tangent. Okay? Now I will be asking some of you to help me out here. If we will integrate the tangent of 5x dx, can we have an outright direct answer for the integral of the tangent? Or do we have an outright integral of the tangent?
No, miss.
No. So correct. Now, if we don't have a direct outright integral of the tangent, what do I need to do with my tangent?
Use
5x.
Pythagorean. The
What?
Di pala miss is sine over cosine.
Okay, correct. Very good. So we will change the 5x tangent here to sine of 5x over the cosine of 5x dx. Okay? Now let's see. Now I have converted to the sine over the cosine function. Now what do you think, looking at it, would be the resulting or the appropriate resulting integral? Or what would be the appropriate resulting function after integration? Or what would be the function that this integral will yield after integration?
1/5 sine 5x dx plus c, miss.
Okay, 1/5 sine, again, 1/5
Sine 5x plus c.
plus c. Okay, another one who has a better answer? Do you agree? Okay, this cannot yield a sine or a cosine. So if you assign your u to be cosine of x or 5x, your du will be 5 dx, right? For this. Now, if the entire thing, I will clear na lang right here. Integral of sine 5x cosine of 5x dx. I will try to rewrite it into an expression that you will see right away what I'm doing. So I will have here sine of 5x times 5 dx over cosine of 5x. I place a negative here, and I place a negative 1/5. What do you think am I doing? Why did I have to complete the one that I have in the numerator? If this is the u, this one is the du, right? The derivative of cosine 5x is negative sine of 5x 5 dx. What I have introduced here is the negative and the 5. Since I introduce a negative and a 5, I need to place a negative outside and a 1/5. That way, I did not alter the original given integral. If this is my expression, a du over u, what would be my answer for the integral now? That would be negative 1/5. I copy this one, the ln of the cosine of 5x plus c. Du over u yields an integral which is ln. Provided that, this is what I'm saying a while ago, provided that the entire u in the denominator should have the complete du in the numerator. To complete it, there should be a negative and there should be a 5 here because the derivative of your cosine 5x is negative sine 5x times 5 dx using chain rule of differentiation. The negative 5 that you have introduced here should be compensated by writing negative 1/5 outside of the integral sign. So the integral of tangent 5x is negative 1/5 ln of cosine 5x. Do you get it? Do you get it?
Next question.
Yes.
Um, if ang cosine 5x mas ang u miss tapos, ay, never mind, ganun.
Never mind.
Yes,
Okay
miss.
na?
Okay na yun. Thank you,
Okay,
miss.
okay, okay. So, we have, may question pa? Okay, problem number 3. This time you need to recall what we have reviewed in the last 30 minutes. You have to do transformation here because you have the product of the secant and the tangent. Okay, now I would like to set aside the 5, or I'd like to write this in the whiteboard. That way I have a bigger space. I'll go to the whiteboard. You have here 5 tangent of 4x secant of 4x dx. Wait, is it 4x or is it raised to 4? Let me check class. Where was it? No. New share. Here. Okay, secant 4x, tangent 4x. Okay, that's correct. 4, 4. So I'll go down to my whiteboard. Okay, you need to integrate this. Okay, so what do? The constant we write before the integral. Okay, and then we copy the function that we have, the tangent 4x and the secant of 4x dx. What do? The tangent has a derivative which is secant squared. It's not secant squared here. So what do? This is what you do. So we copy that 5, you copy, and then the tangent you will convert just like what you did a while ago. Sine of 4x over cosine of 4x. The second, ano gani second? 1 over cosine, right? 4x dx. Do you get it? So I have convert the tangent and the second to these two. Now what will happen after this? You can combine and use the method I used in sample 1. So 5 integral of the sine of 4x dx all over the cosine squared of 4x. What am I doing here, or what are you doing, miss? What do you think am I trying to do here? It's squared. I already took the product of these two. I can write this one as this. So I have 5 integral of, I will write it in this form so you will see what I'm trying to do. So you will have cosine to the 4x raised to negative 2. Then I have here sine of 4x dx. Now, can somebody tell me what I'm trying to do? I wrote the denominator here. Then I have written it in this form. What do you think I'm after? What do you think I'm after? This could be u raised to n, provided that I have the du here. What's the derivative? What's your u in this case? Your u is cosine of 4x. Your n is negative 2. If your u is cosine of 4x, the exponent is negative 2, the du of this u is negative sine of 4x times 4 dx. So what I have set aside here, the sine 4x dx, I will need only to write the 4, and I need to write negative 1 here. Since I place a 4 and a negative, I need to place that way, the same thing here before the integral. That way I did not alter it. Now, I can use power rule because I have u raised to n du. This entire thing is your du. Your u raised to n is the cosine of 4x raised to negative 2, where n is negative 2. I'm going to write the answer here. So if you're going to process this now in terms of power rule, the answer would be, place it here, you copy the negative 5 over 4. If you use power rule to this, that would be cosine of 4x raised to negative 1 all over negative 1 plus c. If this is cosine of 4x raised to negative 1, it's written actually in the denominator. This takes care of themselves. So you have 5 over 4. I can write this as 1 over cosine of 4x plus c. But what is 1 over cosine of 4x? Final answer would be 5 over 4 secant of 4x plus c. So this is the integral of the expression that originally is a product of the tangent of 4x and secant of 4x. Now, I'd like you to check the solution and ask me if you have any questions in the solution or any part in the solution that you may have any question. Have any question?
Um, kasi ang
Yes.
second for x, pwede na lang siya himon nga u. Set u ang second for x para ma-cancel out siya. Like, mahimo.
What will you do? Ano i-cancel?
Like, for example, mas i-use ka u substitution sa tan for x, second for x. Na
Like,
set u as second for x.
okay.
Then, du siya is equals to second for x tan for x. Then, do ka usual, wala lang sa u substitution.
Titing ka makuha sa isa mo ka second? If you use secant 4x as the u, your du will be secant 4x tangent of 4x. Where's this, the other secant 4x? That cannot be used because that will only work if you have a tangent of 4x secant squared of 4x. You can set aside 1 secant of 4x, then the remaining tangent of 4x, secant of 4x will be the du of your secant. That would be correct. But in this case, you cannot assign a u for the entire secant of 4x because the derivative of that is secant tangent. Where will you get the other secant because you already assigned this as the u? You have no other secant to use. Do you
Yes,
get it?
yes, miss.
Oh, so hindi siya pwede nga iseta ang secant 4x as the entire secant of 4x as your in u. Hindi siya pwede. Yes, some more question?
Yes, miss. Yes.
May question? If you're going to ask me, class, this is the only solution. There's no other solution for this. Because there's no other trigonometric expression that I can recall that will process this one, except that you have to convert the tangent to the sine and cosine equivalent. Same thing with the second. And set aside one function, in this case, that's the sine of 4x, to be the derivative of these two cosine. Kung wala ni siya ang isa ho, may ln naman ni siya parehas to sa previous example. Galing kay may-ari ka cosine of 4x, which you need to multiply to the other cosine of 4x, which makes it cosine. By the way, kulang s. That will make it cosine squared of 4x. Now, this is not an ln because the n of the cosine function in the denominator is not 1, but rather it's 2. So you have to use power rule. So this is really the answer for that. Okay? We'll go to the next so that we will have a lot, we can discuss a lot. Oh, where is it? Okay, we go to this one. Secant squared, secant x plus cosine x quantity squared dx. So we'll have this written on here. So the square of the sine plus cosine. So you have the integral of sine x plus cosine of x squared dx. Okay, can I have a suggestion on what we're supposed to do with this? Anyone? That do we do? The sine of x plus the cosine of x added and then squared. Let me check the original given. Yes, it's squared. So what do we do? Any suggestion? You have to expand this class. You need to expand that. So you have the integral of the sine squared of x plus product of these 2 times 2. You've learned that in your algebra. Twice the product of these 2 plus cosine squared of x dx. Okay, I have that. Do you have any question with the expansion? Do you follow? I will do, okay, I will do regrouping class, ha? So I will have here, so you will see what I'm trying to do. So I will regroup. I'll group these 2, plus I'll have this 2 sine x cosine x. Now, why do you think did I group these 2? Or did I put side by side the sum of the square of the sine and the cosine? What do you think is the purpose?
Ay i-value mismo lang namin.
Very good. Yan, ilang ang value siniwan lang, miss. Very good. So I will write here integral of 1. What about this? Ano ni siya? 2 sine x cosine x. You recall an identity equivalent for this?
Ang half angle, miss.
Half angle? Is it the half angle or the double angle?
Double angle, gali, miss.
Okay, the double angle sign. Very good. The double angle sign 2x, you double the angle here, is the equivalent of this thing. So look at this, a very simple integral. So you will have integral of dx for the 1 plus the integral of the sine of 2x, dx. So to complete this integral, you need to assign the derivative of the argument of the sine, which is 2x. So this should be 2, and I should have 1/2 here. Do you follow? So the first will yield an integral which is x. The second will yield an integral which is negative 1/2 cosine of 2x plus c. Because this one will have a direct integral as long as the derivative of 2x is complete. So that is why we introduced the 2 and we placed here 1/2. Okay, so this is your answer for that particular integral. Okay? Okay, let me go back to that part. If you have any question, just butt in. Okay, just ask. 3 cosine squared 5x. Okay. 3 cosine squared of 5x dx. How are we going to simplify this? We what? We set aside the 3. And what do we do with the cosine? Anybody? What do I do with the cosine? Squared. It's a cosine squared. I reviewed a while ago what's the equivalent of the cosine squared. You can convert this to what?
1/2 sine 5x. Right?
1/2. You're right with the 1/2, but what about the numerator?
1 minus sine.
No.
1 plus sine, miss.
No. Oh, squared sa iyo. Squared. Ano ang conversion ng cosine squared? And sine squared. Identity. It's the double angle cosine. So this should be 1 plus cosine of this 5 should be doubled. 10x. You get it? If it's a cosine squared, you can convert it to the double angle cosine. What does that mean, miss? You double the angle of the cosine to get rid of the squared here. That way you can integrate. So that's it, oh. Okay? You double. If this is sine squared of 5x, this is minus. You double the angle of the cosine. So what you do, you place 3 halves outside, and you will have the integral here of 1 plus cosine of 10x dx. What's next? You just have to distribute the process of integration. So you will have 3 halves. We'll multiply it to 2 integrals. One is just dx for this. And the other one is the integral of this. So you have the cosine of 10x dx. So ginapalayo ko para mabalaan nyo kung anong kulang. If this is to be integrated, the cosine of 10x, what is lacking? What do I need to introduce? Can we go ahead integrating this? Or there's something that I need to do to complete this integral? That way I will have right away the corresponding answer.
10.
Okay, you need to place here the 10 and you need to place here 1 over 10. Okay? Then you are ready to answer. So you can now answer your given integral. So your answer will be 3 halves. You still copy that constant. The integral of the dx is the x. And the integral of the cosine is sine 1 over 10 sine of 10x plus c. We can integrate the cosine yielding a sine as long as ang iyan naman sining derivative, its derivative is complete. Excuse me. So we need to introduce the constant 10 here. Excuse me. And divide by 10 before your integral. You have any question here? None? Okay, we go to our problem. So we will have a lot. We can cover a lot. So this one, 1 plus tangent, or rather 2 plus tangent of x squared. I think you will know what to do here. 2 plus tangent of x quantity squared. So this would be 2 plus tangent of x squared dx. What will you do? What will you do? Expand. So you will have 4 plus 4 tangent x plus tangent squared x. That's the expanded form. Okay? Now, you evaluate each term separately, meaning you evaluate the integral of each term separately. So for this 4, that would be 4 integral of dx only. I set aside the 4 already outside. This one, just like what we did a while ago, you will have 4 integral of, I'll change the tangent to sine of x. We'll have dx here over cosine of x. So you would see what would be it yielding. The last one, which is the integral of tangent squared, what am I going to do with this? What's the equivalent identity of the tangent squared?
1 minus secant squared.
1 minus secant squared. Okay. Ma-review tanay ha? Okay ha? So you have sine squared x plus cosine squared x is equal to 1. That was your classmate saying it a while ago. For me to be able to have a tangent, I need to divide by cosine. I divide by cosine squared x. So this is tangent squared x plus 1 is equal to secant squared x. 1 over cosine squared is secant squared x. So you see, Iho, what's wrong? It should be secant squared
Minus 1.
x minus 1. So I'll write here secant squared x minus 1 dx. Okay? Now, this one can be integrated. I'll write it here. That would be 4x. This one is your u. This one should be your du, provided there's a negative sign. And I'll place the negative sign as well here. So second term will have 4 ln of cosine x. Do you get it? You get it? And we'll erase this because that's a review from your trigonometry, how we arrive at. And this one will have to be integrated separately. This one, the secant squared x minus 1. So what do I mean by that is, where's my annotate here? You have to distribute, like this becomes secant squared x dx minus dx. Okay, so you will integrate this and you will integrate this. What's the integral of the secant squared of x? Anyone? What's the integral of secant squared of x?
Tangent x.
Correct, tangent of x. This one is x plus c. These two you can combine. So your last line here will be 3x minus 4 ln of cosine x plus tangent x plus c. This is the answer to that given integral. Okay? Now it's 3:30. I will stop sharing now. If you have any questions, now I will show this one. As you can see here, class, I have a lot here to process. So what I'll do for Wednesday, since you have a quiz on Wednesday, tomorrow I will give you a recording on the solution of the remaining part here. That way you will know, you will be reviewed on what you will answer in your quiz on Wednesday. Okay? So this recording now, I will also share with you together with the solution of the rest of the items that I have placed in here. But for now, I'd like to go back to our whiteboard. Do you have any question? Have any question? None for now. So I will select specifically examples that will tackle on the transformations because these are still elementary, and by parts which I will record. But on Wednesday, on our time, you will really have your quiz number 2, and I will have that recording given to you tomorrow. That way you can listen to that and also study for your quiz on Wednesday. What's the coverage of the quiz on Wednesday? The coverage would be all the techniques that I have discussed so far from techniques of integration part 1 and part 2, because if you look at Canvas, we still have more under it. So we will just have it for the quiz on Wednesday, the first 2 set of slides. Do you have any question for now, class? None so far? Okay, so don't hesitate to ask me any clarification regarding the